do have the same mean length. Um, so what I did was I calculated the mean for both of them. Hold on, this is a lot of very bright, very fast. It's much better. So calculate the mean for each of the populations or each of the sample sizes, sample sizes. And then, so like Devon's was 150.417, Cornwall's was 129.36. They had different sample sizes. So one was 12, one was 11. So what I did was I calculated the t-test of, but for kind of comparing the both of them, if that makes sense.
Yep.
So I did 150. So the Devon one is 150 point whatever minus 129 over the standard error of the first ones. So what I did was it was like, so I calculated the standard error of Devon, which was 22.5.
Yep.
So, but my question was, I did it for both sides. So the first one was like the Devon was like the sample, the p hat, I guess, or d hat, whatever. And so 150 minus 129 over 22, and then got the t value. But then I did the same thing for Cornwall because I was like, I don't know which one I need to be the sample size, if that makes sense. So I did it then 129 minus 150 over the standard error for Cornwall, which was 24, and got, so I got both of them basically. So the first one, when Devon is the, like sample, like I guess, or the p hat, I guess, is 0.91935, and then the second one, when Cornwall is the p hat, so it starts. The t is then negative 0.857. So one, is it correct to be using and comparing both of them? Because I didn't know which one was the like P0, if that makes sense.
Okay, sure. I'll share my screen.
Yeah.
I think like what you did really makes sense. Especially like because you jump from the one sample t-test to the two sample test, and of course the test statistics is the difference of the mean divided by something related to the standard deviation.
Yes.
Yeah. But I just googled the about the two sample t-test. And you can see there, he said there is like a pooled standard deviation. Basically, that's a weighted mean of the two standard deviation because they have different, and you mentioned they have different like sample size. One is 12,
Yes.
one is 13. Yeah. So basically, you can use this formula. It's a ST star pooled. You can use this formula to calculate the pooled standard deviation because it has to do with the sample size with N1 and N2. It's a weighted average.
Okay. So then it's, but then does it matter? So I would use that sample size for the standard deviation. That makes sense. So for this one, so it's, man, I was so confident. I was like, ooh, I did so well today. Maybe not.
It really makes sense. I mean, on your first try, you can do that. You know, you should compare those two standard deviation. I mean, yeah, it's impressive. I mean, pretty
cool. And then N2 minus 1.
So basically, you should plug in maybe N1 equals 12 or 13. I don't know, like 12 and 13.
Yeah, it's 12 and I think it's 12 and 11. Yeah, but
yeah,
okay.
Yeah.
And then, so then my question is, so that makes sense that for the t-test, it would be the denominator would be this SD pooled.
Yes.
Does it matter which one is p hat versus p0? So it would be p hat minus p0 over this standard deviation that we calculate.
Oh, yeah. So normally, So basically, that doesn't matter because that will result in the same number but with different sign, like positive
Oh,
one or negative one.
yeah.
Yeah, but
Okay.
like normally when we write the formula, we use the uh, like our
The p hat is the
calculated
same.
mean.
Yeah.
Yeah, we
Yes. Yeah.
use our calculated mean minus
Okay.
the mu that we want to test. So
Yeah.
that's the one sample test, by the way. Like, but here in the two sample test, it really doesn't matter if like you just calculate the
Yeah.
difference.
Okay. It doesn't matter. Okay.
Yeah.
But now because we have, and we'll have that joint standard deviation using that formula, that will
Yes.
calculate it. So then we can say, okay, I can do this later then.
And then like
Um,
here, by the way, the degrees of freedom would be n1 plus n2 minus 2. It's just in the denominator of this formula. So that would be helpful when you try to find the critical value of t. You go to the t table, you have to find like the alpha and the degrees of freedom. Like in the one sample test, it's just simply n minus one, and it also makes sense. Like in the two sample test, is n1 plus n2 minus two. It's just minus one in both sides.
mhm.
Yeah.
So can't believe this. Um, okay, so it's the weighted. Sorry, I'm just like orienting myself. So yeah, this one. So you're saying because it's two-tailed, we once we find that t statistic result using this formula, what say that again one more time?
And because it's a two sample t-test, right? We have two standard deviation.
Yes.
So we have to find a pooled standard deviation, which is the weighted average of
Yep,
two
which is
standard
this one.
deviation.
Yep.
Yeah.
But once we calculate that, it's not. There's nothing else, right? It's using the, let's say, the mean, which is, it's, as we said, it doesn't matter which one we use because it's just going to be a different sign.
Yeah.
But it's, sample mean for Devon minus sample mean of Cornwall over the pooled standard deviation, and that would
Yes.
get us the test
Yes.
statistics. And then we can say, okay, because of that, we can say whether there's reason to believe they might have the same mean length.
Yes, you should compare your test statistics with the t critical value.
Yep.
Yeah.
Which you can then find in the book.
Yes.
My question is, so then if I'm looking for the t statistic, it would be, would the degrees of freedom be the sum of the, it would use the
Yeah.
sum of the two ends. So it would be 11 and 12. So it would be a
No.
degrees of,
The degrees of freedom is n1 plus n2 minus 2.
yes,
Yeah,
yep,
yeah.
yep. That's what, yep. Okay. So that would change how you're looking at it too. Okay. Yeah. Yeah. Okay. Oh dear. All right. So the next part is the Wilcoxon rank sum test.
Yep.
So do you mind if I share my screen for a second?
Okay.
So after lots of research, I discovered that you need to find the differences between the samples, which I did. So the Devon, like, you basically order them, then say minus, and then subtract so you can see what the differences are. What I didn't understand was because it was a different sample size, I didn't know how to get to like this last one, if that makes sense. Like I wasn't sure, do we not use it? Do we use something else? What
Okay.
do we do with that?
Okay, so first, like you are trying to do the difference test. It's also like a kind of t-test.
Mm-hmm.
But actually, the rank test, I would say, is much more easier than the t-test in like mathematical principle, in
Mm-hmm.
terms of math principle. So, so it's called a rank test because the first step is you need to rank those statistics.
Yep. Which I think I did, right?
Yeah,
They're in
but
order.
the important thing is you should combine those two and rank them together.
Oh, rank all of them together.
Yes.
Okay, hold on. So then, mhm. So it would be, sorry, I'm just putting into the some calculator thing I found online. Sort numbers. So then it would be just copy and paste this back into the Excel. So then, so we did that. So it's now ranked. Sure. It's now ranked for all of them. So, which makes sense. It's count of 23. There's 23 things here. And then would you do the differences of all of them? Is that what you mean? Is it like, I know you,
Wait a second.
guys,
Maybe I will do that in Excel. Um, wait a few seconds.
okay, because I know we're looking for like the difference, and then we're able to say and rank the differences, and then I guess you sign the ranks. So it's
Yeah,
I don't.
I mean, you don't have to find the difference because, um, like the principle of the rank test is, for example, I want to say like my grade is basically the average of my class grade, right? So
Mm-hmm.
what do? I just rank every people's grade, and then I want to see if my grade lies somewhere in the middle. Right, if my grade is on the top or on the
Okay.
bottom, I wouldn't say my grade is similar as my class average. And similarly, I can say like I form a study group with like 5 students, and then I said, okay, so the study group of this study group has a little bit higher grade than the class average. And what do? I just rank every student's grade in sequence, and maybe I find like all of the 5 students in my study group are somewhere at the top of the whole sequence. And I could
Mm-hmm.
say, okay, I have a little bit better grade than the class average. So basically, that's the intuition of the rank test. Um,
So I think there's actually a question. I think I was confused because when I was Googling this test and looking, I think even in the slides, it was talking about the mean, but I think this question talks about the median. Is
yes,
that's
yes,
correct? Like, so it's kind of a
absolutely.
different way to be looking at it then. And okay, so if I'm looking at this and I'm looking at whatever 23 things here, the question's asking, I'm saying, can you answer the question using the sample rank test? So I want to say,
Um,
so I'm looking for the middle number, step one, which is the median. Is that the right step one?
um, so first I would like share the write-up of those tests. So basically, you should rank all those number 97, 102, 107 something. Those are like
Mm-hmm.
top few ranks. Um, should
Yeah.
write those down. So all of the statistics and then number them like 1, 2, 3, 4, 5.
Mm-hmm.
Those are their ranks, right?
Yep.
And then um, I'm not sure if um, that make any sense, but I can find the expected value. So first those ranks they involve like two kind of statistics, and we want to compare if those are the same, like the Devin and Convor, right? So we want to compare if they are the same. So
Yeah.
basically, if all the Darwin statistics lies in the middle something, so maybe we would say though they are actually the same because like one group they are all lies in the middle, another group they have some top statistics, they have some bottom statistics, and they maybe the average or their mean like is somewhere or the medium like is somewhere lies in the middle. So that's the intuition of how to perform this test. But in the sense of the formula, uh, here if you can see this mu and variance, those are basically the formula of this rank test, and you can prove that like easier than the formula of t-test actually. So um,
So you're saying
so for
we
example, um, let's see. I can write this formula like I can spread that a little bit, so maybe that's easier to understand. Um,
so if I'm looking at this, yeah, can you show? I'm not. So I'm looking for the mu, but I don't know what that NA plus
okay,
NB
that's
means. Like, what are NAs and NBs? What would be a good example of that?
it's just like the here. It's just like what you did in the t-test. It's N1 and N2. Like NA is the number
Okay,
of
so
statistics in Devon. N2
okay,
is
so
the
you're
number
saying
in Cornwall.
it's NA, which is 11 for
Yeah,
Devon, for example,
yeah,
and then NB is 12 because that was Cornwall population. So basically, you're saying it's just, and then so then
First, you
you would
could
add the you like, or sorry, go ahead. You go ahead.
I mean, first you could just first write down those formula first. Those are two formulas that you can calculate the mean and the variance.
Yeah. Okay. So it's
Uh,
U equals NA over 2, and then the variance is similar. But the variance, so this one is calculating the variance of A, which I'm just going to say A equals Devon,
yeah,
B
yeah,
equals Cornwall. That was cruel. They could have
yes,
used B and C, or D and C.
yeah.
um,
So basically, I would show like how do we interpret that formula of the mu for the variance. It's like a little bit harder, and if you're interested in how it is proved, you can like maybe look it up somewhere. Um, But firstly, what in the right side of my the formula here? So what I circled here. But
You're not showing me anything. Sorry, I'm looking at the Excel
okay.
spreadsheet.
Okay, wait a second.
Thank you.
That could be nice. Can you see here?
Yes, yeah, I see
Okay,
that.
sure. Sorry for that.
No worries. No.
Right. So basically, this is like it's a times in the middle. So basically, in the right side, what I circled here is the sum of all ranks. Right. If I have like if N1 is 11, whatever 11 or 12, and N2 is 12 or 11. So basically, here in the right side is 1 is like 23 times 24 divided by 2. So that's the sum of all ranks. If you like add up from 1, 2, 3, 4 all the way to 23, you have a formula, right? You have like what you know, it's like a sequence. It's 1 plus 23 times 23 divided by 2. So basically what I did in the right is the sum of all ranks. I just add up 1, 2, 3, 4 all the way to 23.
So I'm not. Why did you? Is that different than what this equation is above of NA plus
No,
NB?
it's exactly the
It's
same. I
exactly
just
the
want to
same.
show
Okay.
like how you get that formula.
And then just making like.
You understand that? So basically those are the same because like you can cancel out the n1 plus n2 like right side here in the in the in the denominator and here in the numerator you can cancel them out and you get exactly the same formula like above said mu equals na plus nb plus 1 divided by 2. But I just want to show like how you get this formula, right? And it can help you better understand like how to perform this rank test.
I don't get. So. I see.
So what I did
Honestly, I
is
don't understand how you do that. Like, so it's and
so
yeah,
basically I
I don't
just
get it.
sum up all the ranks and then I scale it by here n divided by n1 plus n2. If
You're
for
summing up all the ranks. So
yes,
almost, is it like, so 24 plus 20? So it's 23 plus 22 plus 21 plus 20 plus 19 plus 18. Is that what you mean?
yeah, I just sum them
Etc.
all up. That is the things I did in the right from 1 to 23. I just sum all the ranks up. Right.
Okay.
This is how the right side is working out. Is just sum up all the ranks, and then I scaled by n1 divided by n1 plus n2. So n1 plus n2 is just 23 again, and then there is n1. So if you think about it, for example, when n1 equals 1, what does that mean? It's just the mean of all the ranks. I just sum up all the ranks and then I divide it by 23 if n1 equals 1. So that means my expected rank is just the mean, right? So if I only
Which
have
is
one
11 and a
statistics,
half in this.
yes,
Yeah.
that means if I only have one data in like for example the Darwin's, if instead of 11, 12, I only have one data. So if I perform this rank test, my expected mu would be the mean of all the ranks. And that's like my examples before, like how can I say my grade is the class average? I only have one person. I said if I scored the mean of the whole class, then I would say like there's no difference between the class average and my grade. But again, if n1 is not equals to 1, n1 equals 5, or in this case n1 equals 11 or 12 something, that is similar to, as I said, I have a study group. How could I say like my study the grade of my study group is the same as the class mean, I use this formula and I scale the sum of ranks by the number of students in my study group. So basically that's how this formula come from.
So putting it into this example, I understand that you would rank them. I understand that there is the expected average using the rank test would be 11 and a half. I don't understand how you get there from that formula there, because when I'm looking at this formula and I'm like, okay, NA plus NA plus B, NB plus 1 divided by 2 is 11 times 11 plus 12 plus 1 divided by 2, which equals 132.
Yeah, so what you said, 11.5, that's the
rank.
That's the rank, the average of the rank.
Yes.
And here it equals like what N1 equals 1. When I only have one number, that is my expected rank. But here I have 11 numbers, so I should scale that. I should multiply that by 11 or by 12. Right? What do you expect the mean? Like,
what do I expect of the mean? I expect it to be 132.
Yeah.
I'm not sure. Like,
yeah.
I mean, yeah. Right? Like, I think I'm getting a little lost in the sauce here, but right? Like, we solve it. I expect the mean to be 132.
Yes.
I'm now, and then for the variance, I do the same thing, or plug in the numbers. So NA is, so it's 11 times 12 plus 11 plus 12 plus 1 divided by 12. To do the math.
Yes.
Mm. Yeah, 3168 divided by 12 equals 264 is the variance. So, and then the whatever standard deviation is square root of that, which is 16.2. But so when I'm trying to answer this question, it's saying I have ranked everything. I have plugged in those numbers to find the expected mean and the expected variance. And then so then I plug it into the test statistics again.
Yeah.
So, and then it's like, so the expected mean is the 132.
Yeah.
And then, but then which is P0, right? P hat is then what's actually 11.5, if that makes sense. Like the ranking of 11.5. So
like 132. So actually this is simply 11.5 times 12.
Mm-hmm.
Right, because you have 12 statistics and the mean of each one is expected to be 11.5. So basically that's how you did this 132. That's the mu. That's the expected rank. And you also get the standard deviation.
Yes, which is
square root that variance.
Yeah, which is 16.248, whatever.
Then I need an actual number. What's the rank? What's their actual rank?
So
because I already ranked them. You can see like in the Excel.
Yeah, in the Excel,
it's like
that's
1, 2, 3, 4, 5. Some of them are Darwin's data. Some of them are Cornwall's Darwin's, and some of them are Cornwall's data. And
so we've ranked all of them together. When I'm looking at number ranking 11 and 12, it's 133 and 135. do I use the middle of that? Like, because it's 11.5 ranking is the actual one, so it's 134. I can share my screen if that's helpful.
Okay, sure.
Oh, you're, yeah. So it's 130. So ranked, all of them together, 23 of them are here. I ranked them all. I know I'm looking for 11.5, which isn't a thing.
Okay,
So
you should calculate the actual mean, right? So where is the 97?
oh,
What is the
okay.
first one comes from? Which statistics it is, right? Maybe it's
Wait.
from Devon, maybe it's from Cornwall.
So you want to know the average of all of these? The actual average.
No. The actual rank.
You mean,
So I expect,
why are these not the actual rank?
because
That's
here I expect the mean of Devon is 132, right? That's my expectation.
Mhm.
But what is the real things? What is the real rank of Devons?
So like Devon, do you mean like this? Like you want me to like identify which ones are Devon? And then
So you add them up, and that is the real rank, the sum of the real
uh
rank.
rank.
You
Jeez.
just calculate the expected rank. And in order to perform any statistical test, you should like find the difference between the true mean and the expected mean. Right here is the true rank and the expected sum of ranks.
163, 169, 170, 74, 182. Okay. So now I have all of them. So I'm now going to add up together. So it's equals 4 plus 6 plus, is this what you mean? Just not
Yes.
11 plus 12 plus 13 plus 15 plus 17 plus 18, 19, 20, 21, and 23. 179.
Yeah, like
So,
intuitively, if
and
you
then
think about
divided
it,
by,
like
oh,
yeah,
go ahead.
if like all the Devon's data
Oh, this
are
is it.
on the top few list of this sequence, you wouldn't say like those two statistics are exactly the same, right? So
No.
basically, this rank test is if like all you number you assign the the Devon, if they are like in the middle, like or they are like spread in this sequence, they're very widely spread in this sequence. Some of them are in the few top ranks, some of them
Yeah.
are in the bottom ranks. I would say maybe their results is exactly the same as a Cornwall's result. But here, like at the first glance, I would say like maybe we will reject the null hypothesis because there is a lot of Devon statistics in the bottom, right? If you
Yep.
just look at it, there is like more in the bottom than on the top.
Yeah.
So maybe I would say the Darwin statistics maybe it is higher than the Cornwall's statistics.
Yep.
That is like my first guess. But
Yes.
yeah,
But then you run the calculation for the
yeah,
t-test, which is
yeah,
179 minus the 132 divided by the standard deviation,
yes.
16.24, which gets you a statistic of
That is a z-score,
2.8. Oh,
by the way. That is a z-score, right? You use it's
and
like the,
remind me why we're using a z-score, not a t-statistic?
because it's like the x minus mu divided by standard deviation, right? We call that like it's a z-score. The t-score, like we have a large number, we should have a weighted standard deviation. It's either the standard error or in today's case, it's a pooled standard deviation. But like in a z-score test, it's just the denominator is just the standard deviation. Yeah.
Okay. Oh, yes. Actually, that makes sense. It's just the same. Okay. So then you have the z-score of 2.89, which is very high, which is like what? So, and this is so we're trying to see if it's equal. It's a two-tailed test, similar to the first part. So the z-score of 2.89 is very high, which is about 2.9. If I'm looking at the table, which is like 0.996%.
Yeah. So you.
So it's very, yeah. Because the odds of them being the same are very. Okay, well, thank you. This was helpful. Okay, so then we did that one, the WRS test, and then so if I'm comparing the results, I haven't finalized my results in part A because I'm using the pooled standard deviation, so I'll do that later. The next question is I'll stop sharing my screen for a sec. So when I was doing this one, so basically you're trying to see if the cream has improved women's skin.
Yeah.
The eye is improvement and is no improvement. What I'm trying to do is the P0 or PO, I don't know, is 0.6. When I'm looking at the data, my counting got me to 24 women out of the 33 had improved skin. So that's the P hat of like 0.727.
Yes.
So then I did a t-test. So the 0.727 minus 0.6. I calculated, so this is a t-test, so I calculated the standard error, not the standard deviation. So is that correct, first of all?
Yes. Yes. You could do
Probably.
that, but that depends on how you calculate the standard deviation or the standard error.
So I did it was P times 1 minus P divided by N, and then a square root over all of it.
Yeah. So that is correct.
Yeah. So then it would be 0.853. So then I got my T result of negative 1.488. Because so this is one-tailed because we're trying to see an improvement.
You get a larger number of the standard deviation. I don't know, but like intuitively, I think like your number is too large. It's like P times 1 minus P divided by N, right? That's the
square root.
Okay, so basically your P is 24 over 33, right?
Yep, which is 0.727.
Yeah. So
and then
what's the result again?
My result is negative 1.488 for the t-test.
And what's your standard deviation?
0.0853.
I guess that's too large.
I did something wrong. Okay, let me see. So it's 0.6 times 1 minus 0.6.
Oh, you use 0.6. No, you use 0.727.
Why?
Because that's the variance of your expected number of your P hat.
Oh, because it says p hat. Oh,
Yeah.
okay. Okay. Darn. 0.727. Then 1 minus 0.727. .273. It's still divided by the n, which is 33. Is that true? It's n is 20 is 33, right? Not
Yeah,
24. Yeah.
Yes, it's a total number.
By 33. Ooh, it's tiny. Okay, hence why you said it looked really small, so it's 0.00601. So it's then redoing it again. It's 0.727 minus 0.6 equals 0.127 divided by 0.00601 equals, oh wow,
Remember
21.
remember to like square root the. Yeah.
Dang. Thank you. So okay, so now it's 245 then. Okay.
Yeah, so it's like p hat times 1 minus p hat divided by 33.
Yes, and
That's
then
the
the square
value
root, which I forgot
you
to
square
do.
root it. Standard
Okay.
deviation.
So then it's 0.127 divided by the 0.2451, which equals the t value of 0.518. So with the t value of 0.518, that's, I need to go look at this. With the degrees of freedom of 32, I mean, like, yeah,
I think like for this one, you still use the z-score because the.
But I found the standard error.
Yes.
Is it because the sample's not big enough?
The sample is big.
Yeah.
You find the standard error. I wouldn't say it's like a standard error because this is remember this is like a binomial distribution.
Mm-hmm.
And you use the formula like p times 1 minus p divided by n square root.
Yep.
I would say it's a standard deviation of the p hat.
Okay.
So here I would use the z-score in this test. Like I would argue the denominator
Okay.
is a standard deviation of p hat.
Okay. So standard, okay. So, okay, so it's 0.518 is the z-score, not,
Yeah.
and it's one-tailed because, as I said, because we're looking at if the skin actually improved or not.
Yes.
So 0.518, I'll use just 0.5 because that's as close as it's going to get. Mm, it's like 0.3085 is about right.
That's your p-value. 0.8.
0.3085.
0.30. So it's like 30%. You cannot reject it, right?
Uh,
24 over 33, I guess. I guess you should reject the null hypothesis. Wait a second.
3085. So since the p-value is greater than 0.05, is that
Yeah. So
we would say not
you
reject the null
reject it.
hypothesis. Yeah.
But what's your standard deviation again?
0.2451.
Could you like recalculate it? I get a much smaller one.
0.727 times 0.273. Is that right?
Yeah.
Divided by 33.
Yeah.
And the square root. Oh, fuck. 0.07755.
Yeah. Because what I find, like the 30% p-value is too high. Because like if you think about it, you have like 24 of them increase the scan like 24 over 33. It's a very large proportion. And even though you cannot reject the null hypothesis, the p-value could be not like too higher than 5%, I think. So if you get a 30% to 30%.
Okay, so doing this one more time.
Yeah.
The standard deviation is 1.637. The z-score, the z-score is 0.1637.
And the z-score, I guess it's like 1. It's higher than
1. 1.6. Yeah, 1.637. And then, geez Louise. Point. Which then gives me the p-value, trying for the 10th time, 1.637. Z-score is 1.6, which is about 0.0548, which is still greater than the assumed alpha of 0.05.
Okay, so it should be close, like whether you reject or not. The cutoff is.
That would make sense.
Yeah.
So since the p-value is greater than 0.05, we would not reject the null hypothesis that women's skin improved with the cream.
Yeah.
Okay. So then I feel bad for you grading this later when you're reading my bad handwriting. Then the sign test. So maybe I did this one right. Let's see.
Okay.
So I did. Hi, Paris. We're just starting number 3, if that's all right.
I have different questions, so you guys can go ahead. Hi, Victor. I got your email now, so I know I owe you a homework.
Okay.
The one that you couldn't read. Nice to meet you.
Yeah. I mean the thing is, like for the second homework, I cannot open it, but just because you sent me an email in advance that submit the homework, so I just grade based on your email submission. But like for the homework for the homework 3 or homework 4, I think, like what I said in the email, like I couldn't open it. So but I'm good at you can submit the homework like by photograph, by like any kind of things. You don't need to convert that to a PDF. So
Okay.
yeah, so later in this semester you can like maybe use a different tools to submit it.
Sounds good. Thank you.
Yeah.
Cool. hopefully we'll go through this quickly, Paris, and then you can have your
Take your
questions. So
time.
don't
I
worry.
literally just got home rushing, like, I gotta get on this call. So take your time.
No
I probably
worries.
need water. I'll be right back.
No worries. Okay, so the third question is asking for the sign test, which I was unfamiliar with and before. So what I did, so the question is, what is the test statistic? What is the reference distribution? What's the p-value? And we're using the Darwin data, which are in the slides.
Yes.
What I did was, I will share my screen if that's okay.
Sure.
Okay, so I copied the cross plants and self-pollinated plants growth from the slides. Then you calculate the difference, and then you look at the signs for the differences.
Yeah.
So my expected P0 is 0.5, like, so basically like you're expecting no
Yes.
growth.
Yeah. There's
But the
equal
P hat,
chance.
yeah, there's equal chance that, yeah, there'll be, self-pollinated or cross-pollinated. The null hypothesis is that they
Yep.
would, there's equal chance that they'll be a higher, grown taller or shorter, I guess. So the expected P0, I don't know, is 0.5. Then the P hat, looking at the sign test, is 13 divided by 15 because we had 13 positives out of the 15 samples. So it would be 0.866. So then what I did,
No, I think like your p hat, right? Actually, the p hat would be even smaller. Because this is a binomial distribution. So what's your p hat? What's your like calculated p is actually like
so
it's a
like the
binomial
actual,
problem.
so you mean like the average of just the differences generally?
No, I mean you should look at the sign, right? So because as you
We'll
know,
get the sign.
yeah, the expected sign of like positive or negative is just 50%. So what is the
Sure.
probability of getting 13 positive tests out of 15 positive tests? It's a binomial.
So you mean we expected it to be 0.5, so how much more it is than 0.5?
It's like tossing the coin, right? So here,
I was
like,
never good at those examples, so
okay, like we have 15 coins here. Like it's a absolutely fair coin because
yes.
like it's equal chance of positive or negative. You have 15 coins, and the probability of getting like 13 coins is very, very low. It's absolutely lower
So do you
than
mean like the
13 over
0.5
15.
to the 15th or whatever? Like I know we do that for the chances for,
Yeah, that's exactly what you're doing, but it's like you understand that's a process, but it's like not a 15 to the like 0.5 to the 15. You use that formula when you study the binomial distribution. Like, what is the probability of getting more than 13 heads out of 15 toes?
I don't know.
Wait, hold on. More than 15. Wasn't that like one of the first examples that we did?
Probably.
I think maybe.
No, you're right. So sorry. In terms of, yeah, like the gambling odds, if a gambler offers you to play, like something similar to that.
Yeah, exactly. Like I could walk you through like what is the probability of getting 13 positive signs. It's 15 choose 13 times 0.5 to the power of 13 times 0.5 to the power of 2. Right? If that reminds you guys something, it's just you have already done that kind of example a lot of times actually.
So I think the
Like
reason
the
I
n
joined today,
factorial thingy? Is that what you're saying?
yeah,
Like,
I'm
where
about
is
to.
that?
It's like you have to take the probability of the odds it happening and the odds of it not happening on this formula right here.
Hold on one second. Yeah, that one.
Yeah.
Okay. Thank you. Hold on, let me write that down. It's can you show that again one more time, Paris, please?
Yeah, I can text it to you.
Yeah, that's fine. N factorial over n minus x.
But
Factorial
I
x
can send you
whatever.
this because it tells you like it tells you what each thing is.
Yeah.
Nothing.
So
You want me to send this to you?
yes, please. So we're now trying to find the odds of it being out of 13. Man, this is Victor.
Yeah.
I don't like statistics. So we then do, so it's 15 factorial over n 15 minus 13 factorial times 13 factorial,
Yes.
and then times that p to the x, which is 0.5 to the 13th,
Yeah.
times q, which is
Also 0.5.
it's because minus p.
Because the odds of it happening as that's
And
all.
then to the n minus x equals 15 minus 13 again, so to the second. So, okay. Chloe's so excited. I'm like, man, I totally got this homework this week. And every single time I'm like, no, I didn't. 15 times.
Yeah, I mean it's awesome because what you did like compared with your fellow classmates is like you're getting way like you're getting way better than like many of your fellow classmates, and
Definitely not, but thanks.
yeah, like it's pretty cool to like yeah, you actually did everything like before the office hours, and yeah.
Yes, but I did it all wrong, Victor. It's not helpful when I'm doing it all wrong. Okay,
I mean,
so
it helped a lot. I mean, because
yeah.
you're actually trying to do it, and sometimes you really get a point, right? Sometimes the answer is wrong, but your try is like, yeah, it means something.
Yeah, but it's killing time. I don't have time for this. It's 210. Okay, so 210 over. I don't have time to spend 4 hours on homework every week. So then times 12 over what's 12 factorial? 12.
There's a video on YouTube that really helped me that instead of comparing like cost coins, it does like Fanta, purple Fanta versus orange. And it is so helpful in a way to not think about stupid coins. I don't know why.
If you want to send me that, that'd be great.
I feel like I just need your number, so put it in the chat. But I have a couple of videos that have been helping me.
That'd be great. So this is over.
Excel are bad with like dealing with
Can you-
large numbers.
Yeah,
Like
jeez.
I don't know like
It's
if they can
annoying.
calculate 0.5 to the power of 15.
I know. That's what I was like. Uh-oh. So how do I do this? This is getting hard. It's factorial. So I know the formula, but I'm now like, shoot,
Okay, so
it's gonna take forever to
basically
calculate.
the probability of the positive sign greater or equal than 13, which means 13, 14, and 15.
You have to add it together, right?
And what was I doing?
You just did what is the probability of getting 13 positive signs out of 15 positive signs. But then
which is the formula Paris just showed, but I haven't finished calculating that because it's taking me forever. That's what
okay, so if Excel can't do that, maybe you just Google calculator or something, or if you have like a statistical calculator, it would be better.
It comes up on.
So I'm like, it's just taking me a while to just get it because it's just, hold on.
Okay. Victor, I had a question for you.
Okay.
Not homework related. But Grace, just so you know, I am working on something. I'm just super behind in life. Hold on. I started working on, let me find it because my computer crashed. it'll be funny if it just, but I'll look into that in a second. I have no idea what happened to it. Recover unsafe. So we're all struggling with the same thing, Victor. Like, let's just say we have a class and we learn about binomial versus Poisson versus whatever. At some point, if we go to Google and we understand what each variable is, it is easy to be able to plug it in. What I think we're all struggling with is understanding what distribution model we should apply to a specific question. So I had a study session yesterday with Paloma, and again, we really do have the same questions. So if I were to create somewhat of a chart, like a tree chart that says, okay, whether, I don't know which one goes first, whether it's independent or dependent versus replaceable or non-replaceable. Like, if we follow some type of structure, will it lead us to what model we can use? Is there something like that we can create together so that way we can reference that? Because I think that's what we're all struggling with.
Okay, so I would say, because we don't have too much models. So what I think would will help the most is you understand some traits. You understand some characteristics of each
one.
model. Yeah, because we only have like binomial, hypergeometric, Poisson. What else? I think basically you have these three.
But also the other one where it's like it deals with, what is it called? 1 second. Where we look at, like, if the Boyle inequality, don't we have to do that one too?
Oh, you have like another geometric. Is that exponential distribution?
No, this one where it's like where something is like and or greater than.
And or greater than?
Like if it says, oh, what is the problem? Like sometimes this one.
Yeah.
That's still part of it too. So that one I think is a little more clear because you'll know when you have to use that one. But yes, in terms of the other three, you were saying that's what I was trying to do in the tree chart in terms of its independent versus dependent, with replacement or without replacement. Those seem to be the characteristics that apply to different.
Yes. Yes. So, but I think you got the point already, right? So first, all of the statistics, like all of those distribution models, require independent trials. Binomial, hypergeometric, or Poisson. They're all independent.
But like when, for example, if you were to answer some of these, it's without replacement. They're all, I get confused with the replacement piece because because I feel like that's independent if it's without replacement, correct?
Yeah, like, okay, I understand. I got you. Like there's like a little bit like two concepts about dependent and independent. So, okay, I understand your point. Okay, so what I said independent, what people say independent is that the result of the first experiment doesn't influence the result of the second experiment.
Now stay there. So if it's without replacement, doesn't it influence the second one? Because now you're taking out something from the sample set.
Yeah.
So in a way, they're not all independent because some of these you're taking, you're not replacing it.
Yeah, definitely. So that is the point. That is the point you said. So keep that in mind. So and by the way, that is a hypergeometric distribution, right? If you just pull something out and you do not replace it, then the probability, the result of your second experiment will be influenced because you have already pulled one out, and so the probability of the second one will change, right? So that is the standard hypergeometric distribution.
Okay, so now I'm a bit clear. That only applies to that model. It doesn't apply to the binomial model. It's only that.
Yes.
Okay. I feel like it's small things like that that I just needed to get clarity on. Grace, do you have a question before I jump into the next one? Or you're still calculating?
Yeah, yeah, no, I got a p-value that seems wrong.
The p-value would be like you should add up the probability of getting 13 out of 15 and getting 14 out of 15 and then getting 15 out of 15. You should add up 3 probabilities.
But those are going to be like, so I did it wrong. Like I did the first one wrong, which is why I'm in trouble. And you see that?
Yeah, you get a right formula. I mean, you get a right formula. It's just, 15 factorials over 13 factorial, 12 factorial times 0.5 to the power of 15. You get the formula right. And
But I'm getting it, but then I got 13,300 whatever.
It shouldn't be wrong, but it's like just a huge calculation step. That number, by the way, that number should be extremely small because you use
Right?
like, yeah, you use a number times
It should be
0.5 to the power of 15. That is a very small number.
Mm-hmm.
I can help you calculate that maybe.
But so you're saying we do this for 13, then 14, then 15. We calculate all 3 of them together to then once I get all 3 of them together, if I add them all 3 together, once I get this calculation
Yeah,
right,
that is your
which,
p-value.
might be forever. That's my p-value.
And that
then
should be extremely small. And you will definitely reject the null hypothesis.
So yeah, so it should, and then you do the t-test of whatever point, whatever it is.
You don't have to do t-test anymore because that is already your p-value.
It's already the
reason
p-value.
you do a t-test is you want to find the p-value and to see if that is greater or less than 5%. And here your p-value would be extremely small. And that's more than enough to reject the null hypothesis.
Yeah, and say that the plants, whatever they were, grew more like at a significant rate. But so I just need so I have to find the p-value of the 3 of these. Okay, then I will just go do this. I will bother you all later.
I think like the first one is the probability of getting 13 positives out of 15 is 0.0032. You can check that.
Okay, so then
you should calculate what is the probability of getting 14 positives and 15 positives.
Then you add them together and you get that p-value, which is very small, which means you reject it. Okay, so I know how I have to get there. I just got to go get the right numbers. All right.
Yeah.
All right. I'll see you all later.
Sure.
Thank you, Victor. You're very helpful and very patient. Much appreciated.
Sure. Bye.
Can you teach the class? Thanks.
I'm sorry?
I'm like, Victor, can you teach the class? Thanks.
Yeah. Bye. Have fun.
Bye. Okay. I almost lost my PowerPoint. I found it in temporary. So I just want to show you what I'm working on, and I'm gonna share this with the whole class. This is what I'm gonna focus on today. Share screen. This one. 1 second. All right. Okay. So I'm doing like a Paris Cliff Notes where I am just like starting with the foundation, the statistical terms. I'm going to put the symbols on here. And here I'm going, is this important? Because the professor said, write this down, make sure you know that the empirical rule is that, like, he told us to remember 68, 95, and 99.7.
I mean, I can remember that, but you have you have a z-score table, right? You don't have that, you can Google that. So basically, that's the probability of finding a statistics, which is one standard deviation from the mean. It's the probability is 68.27, and two standard deviation from the mean and three standard deviation from the mean. But you can always look at the z-score table, right? That is exactly the same as you get like z equals 1, the z-score, the probability of z equals 1, the probability of z equals 2, the probability of z equals 3. Actually, it's less or equals to 1, less or equals to 2, less or equals to 3.
He didn't really, I don't think he really understood how to read the table. So let me just pull one up. So should I put a Z table in here? I would like for everyone to have a one-stop shop instead of Googling where they can find everything, because as I'm partnering with Grace or Paloma or whoever, it just hasn't worked out the timing to like partner with you, but now I will be going forward to have one document where we have everything. You know what I mean? Like, because sometimes the professor slides, to not anyone's surprise, it's a little bit not clear. So if I look at a z-score table, like it's a lot. So I just want to be able to understand how to read it.
Okay, so I'll go over that.
Let me stop sharing because now it's gonna not share my screen. So let me do that. 1 second. Jesus. Yes, you can see my screen now, right? This is it, right?
Yeah, exactly.
Okay, so Z is what again? Sorry.
The formula of doing Z is you use your number divided by the expected mean. Your number minus the expected mean divided by standard deviation. Right, that is a formula for Z.
Hold on. Let me see if it has it here. No. What is Z? This one.
Yeah.
Okay, I'm adding this to the PowerPoint. All right. Do we have to calculate this type of stuff on the midterm? I mean, on the final?
Yes.
Okay.
Maybe
so this is
even
going
harder.
Maybe even harder?
Yeah.
Okay, so this is it. See, he overlooks these things. Like we spent 5 minutes on this and then we moved on.
Yeah.
So this is the problem where okay, so I'll add this to the PowerPoint in terms of this formula, but how does this get harder?
I mean, you could get a harder question, right? So if it's a Z, it's if the question is about the z-score test, I mean, it can't be too hard. But I would say in the final, maybe you're doing more with t-test and with like the regression analysis. Like later you will.
Oh, this is not now. This is later on.
Yeah.
Okay, but this is the thing. When we get there, we're still not clear on this. So then it adds to the confusion. You know what I mean?
Sure, I understand that.
All right, so this is just a Z. What do we call this?
This is a formula for z-score.
But z-score has to do with the data set, right?
Yeah.
Okay, formula for z-score. And then I'll change this. Z table for data set distribution. Is that the best way to say it?
It's just like a z table, I would say.
But like we're trying to understand what, like the Z table tells you from the standard deviation where the probability of the data will fall, correct?
Yeah.
So is that another way to say Z table for data set distribution or no?
I would say it's a z table for. So z table is always for normal distribution.
For normal distribution.
Yeah. And why you can use a z table for your data set? The reason is the central limit theorem, because as long as your data gets bigger, like you have 30 observations or even higher, you can apply to the central limit theorem, right? So no matter what the distribution of the data set you have, when you observe more than 30 observations, then your observations will be very close to a normal distribution. So that's why you can use the z-table.
More than what, 30, you said?
I think it's 30, but
Double check that.
maybe like over 15 or even 20 is okay, but it's just like in terms of probability. But I would say like sometimes in this class you will use the z-score table.
Okay, get it. Thank you. So I will plug that in there. Okay, so with that said, thank you. Let me, if I go back to this, okay, so this is the formula which X, all right. So based on what I get for Z, then am I looking at Z, is the value there? Then I go down. Okay, this makes sense now.
Yeah.
What was my next question? All right, so I will add that in there. And then I will add in terms of what the attributes are, or like what makes a binomial distribution where the odds are even, and I mean the probability of each outcome is even. And what was the other one?
Independent.
Okay.
Yeah.
And that's it, right?
Yeah, that's it.
And then for hypergeometric, what is that one? That qualifies it to be hypergeometric, because sometimes we get confused.
Basically, that's the result of the second experiment will be influenced by the result of the first experiment. You're pulling things out, not replaced.
So it's without replacement. Okay.
Yeah.
And then the Poisson, which if there's two factors, what will you say they are?
Yep.
For the last one. Yeah.
Okay. So basically the Poisson is similar to the binomial. However, the number is very, very large, and the probability is very, very low. Right? So basically, if you have more than, I would say, 50 or even 100 observations, you're tossing more than 100 coins, for example. And then the probability is very low. Like when you toss a coin, if the probability of getting a head is like 0.005, if that is the case, then it's subject to a Poisson distribution. So basically, it's the tricks, the characteristics is similar to the binomial. Each probability is the same plus independence. However, it needs a stricter restriction, which is we need to find a large number of observations plus the standard chance, like the probability, is very, very low.
That makes perfect sense.
Yeah.
Okay, I will add to this. Can I send this to you before I send it to the class?
Okay, I'll check that. So basically, why you can't use a Poisson distribution when you like tossing 1,000 coins? It's because the probability of getting a heads or getting a tail is 0.5. It's 50%.
Yeah, so that's high.
That is so high. You cannot use a Poisson to like estimate the binomial distribution.
Okay, perfect. But, I feel better now.
Yeah. So one example is you buying lotteries. That is a perfect example of Poisson distribution. So if you buy like 1,000, 10,000 lotteries, and your probability of winning is like 0.0005 each time, right? You win like a huge prize, then that's a perfect fit of a Poisson distribution.
Okay, that's perfect. The second question I have for you is, where can we find like as many practice questions as possible that are very relevant to the final? So that way we can just get in the habit. Similar, like if you were taking a GMAT where it's very focused on very specific types. Do you have any pointers on that?
I would say the problem in your textbook.
Yes, okay.
But definitely you cannot finish all of them. It's too many. So I would say you should like Professor Bartman is giving you like practice problems, so not much, right?
Right, that's the problem. It's
So
like,
you should ask them. I will ask him as well. I will send him an email like
yeah,
saying,
this was perfect because I'm still going back to this to make sure that I can do this unassisted.
yeah,
So that's the thing, like, there's 16 questions on here that the whole class definitely cannot breeze through it on their own. So it's like we need to be able, obviously, to breeze through this on our own come the final. So the more of these that we can get, literally at least like 30 more, encompassing everything that we can have on the final, at least 2 versions of that. We want to take that on our own, like not having an expectations from you or him to get us through it, but that we have something to reference as a clear example of expectation. But the last thing we want is to go blindsided into the final, expecting one thing, and then it's another, and the whole grade is based on this one test, aside from the homework, you know?
yeah.
So that's what we're all looking for. At least I am. No, most of us. When I talk to Oliver and Paloma, we all want examples. So this was great because it's like literally very focused on what we're learning and the text. So we just want more of these, you know.
Okay, sure. So yes, I will send him an email and like you guys can also like ask him about some um, general questions about the textbook problems, or like you can ask him to give you some recommendations of like which problems is worth doing. But the textbook is a very good resource, and
Right.
yeah, yeah.
Okay. What, and my class wants to know, what days do you have class?
What day do I have class?
Yeah.
So
They want you to come out to happy hour.
yeah.
Are you free Wednesday?
Yes, I am free. So in terms of like, what do you mean? You mean after class something?
Yeah. So Bartman came out with us like 2 weeks ago. So now they want you to come out. And they told me to ask you.
Sorry, Bartman, what?
Bartman went out to have drinks with us. Now they are asking me to ask you to come out and have drinks with us
Okay.
on
Bartman
Wednesday.
have drinks with you guys. Okay,
All
sure.
of us. Yeah, it was really funny.
Okay, sure. So yeah, I am available on Wednesday.
So should we send you an email or text you? How do you want us to do this?
Yeah, definitely.
You want me to email you on Wednesday right before class? Like where we're gonna be? We're probably going to Half Pint.
Oh, so you mean? Oh, I mean, so you guys mean like you didn't go to the classroom?
No, we did.
Yeah.
When class was over at 9 o'clock, the professor came with us to Half Pint. So they want me to invite you.
Oh, definitely. So I will come like maybe at 9 o'clock, just
Okay.
to the classroom.
No, we want you to come to Half Pint. We can leave together.
Yeah, that's my
Okay,
point.
perfect. Yes, come to the classroom just in case. All right, I'm telling everyone. I'm serious. Where they asked me to ask you.
Okay, sure.
Because they feel like we're really thankful for you. Because you help us. The class is really hard to understand. So we all watch the YouTube videos or give each other's notes from this discussion. So that's why I'm doing this PowerPoint to consolidate everything with hyperlinks and everything. So I'm gonna try to button this up and send this to you because I don't want to send out the wrong information. So I'd rather you look at it spot check it so that way we can have a good reference.
Yeah.
And be as prepared as possible for the final. So
Sure.
thank you for your time, and I'll see you on Wednesday in class, and then we'll have a drink.
Yeah. Sure.
All right. Thank you. Bye-bye.
Bye.
Bye.
Have a good day.
You too.